Joseph Somsel from Toshiba Westinghouse, who's going to talk about the current state of commercial nuclear power. The hook for you guys is that this dinner meeting is always held at a very nice restaurant. It's Alfred's Steakhouse in San Francisco, and we subsidize the students. So I think there's some students in here who've actually attended these. For $10, you get an amazing steak dinner, or if you don't like steak, salmon or something else. So it's a really good deal for students, and you get a nice talk afterwards. So if you're interested and you want to find out where this place is or how to get there, contact me after class. It's easy to get there by BART or drive over. There's usually a big group of people who drive over and you can get a ride. So that's this Thursday at 6:30. Okay, what else? Okay. Any questions, comments? Okay, let's do some science and engineering. So we were beginning to talk about the nuclear force, and we talked about the four forces and how the strong force is one of those four. If I imagine I have two neutrons and I bring them close together, what are the forces that they will interact with each other by? Two neutrons. Strong. Gravity, right? Weak. How about electromagnetic? How come? Why not? They're electrically neutral. It turns out, that's almost the right answer, they will interact via the electromagnetic interaction, as we're going to find out, because although the two neutrons are both electrically neutral, they have electric charges running around inside them. Remember, there are those quarks that are running around inside. And as we're going to see probably Wednesday, the neutrons and the protons have magnetic moments associated with them due to those electric charges running around inside. And through a magnetic interaction, the neutrons will interact a little bit. But in general, we neglect that in this discussion. So the weak interaction, the gravitational interaction, are incredibly weak. And on the scale we're talking about in nuclear science, we're going to neglect them. So what's being shown here is strictly the nuclear part of the interaction. So it's the nuclear potential between two neutrons, which is shown here. And it's being plotted as a function of the separation distance between those two neutrons. And a couple things we've already talked about, one of which is that the range of the nuclear force is very short. So if I have the neutrons far apart, where far might be an angstrom, typical separation between atoms, the nuclear force plays no role, because the range of the nuclear force is on the order of femtometers, or 10 to the minus 13 centimeters. So at big distances, there's essentially no nuclear potential. As we bring the two neutrons together, that strong nuclear force leads to an attraction. Okay, over that short distance, the strong force is incredibly strong, hence the name, and it leads to an attraction. And you might think that the two neutrons would like to basically sit right on top of each other, and so that attraction would just keep growing until the separation is zero. But in fact, that isn't true. The neutrons and the protons, it turns out, are fairly rigid objects. They don't like to be compressed, and so they don't like to sit on top of each other. And the way that manifests itself is this attractive force reaches a maximum of attraction, which looks like negative on this plot. And then it starts getting less and less attractive and turns repulsive. So if you push neutrons or protons too hard, they'll actually repel each other. Not because of the electromagnetic force, but because of the strong nuclear force. So the strong nuclear force is a lot more complicated than the other forces we've dealt with, in that with gravity, it's always attractive down to zero distance. There's only one sign of matter as far as we can tell. All masses have a positive sign in front of them, so gravity is always attractive. With electromagnetism, we have plus and minus charges, but if I have two plus charges, they will keep repelling each other regardless of the separation. And if I have one plus and one minus, they'll attract each other regardless of the separation. But here you can see it's more complicated. And as we're going to see over the next few days, the nuclear force is a whole lot more complicated than you thought. It depends on a lot more variables than the electromagnetic or gravity do. And as a result, the nuclear force is so complicated, we can't actually calculate things from first principles. So we can't take that potential and grind it through Schrodinger's equation, and calculate the energy level diagram of lead-208. I mean, it's simply not possible. And you'll see why, and you'll get a feel for the approximations we have to make along the way to let us do the kind of calculations which are possible. And we'll sort of show that as we go. Okay, So this strong nuclear force, together with the other forces, lead to this binding energy curve that we saw previously. So remember what we're doing here is we notice that if we have a complex nucleus made out of Z protons and N neutrons, and I measure the mass of that nucleus, it weighs a little bit less than the sum of the masses of the neutrons and protons that go into making it, and that's because of the strong nuclear force leading to binding. And this binding energy, if we take the total binding energy of the nucleus and divide it by the sum of the numbers of neutrons and protons, we get this funny curve. It starts out low, it reaches a maximum, and then it starts falling again. So we want to try to understand the origin of that a little more. And let's think about what goes into binding a nucleus together. So this is a cartoon of what a nucleus looks like. It's made up of Z protons and N neutrons. And first of all, because of the strong force being short range, a given nucleon, and here when I say nucleon I mean either a neutron or a proton, it interacts most strongly only with its nearest neighbors. So the idea is, let's say this is a neutron sitting here. The range of the nuclear force is a few femtometers, and I'm imagining this is a big heavy nucleus that's maybe 10 femtometers. So that a neutron over here really doesn't feel a neutron way on the other side of the nucleus via the strong nuclear force, because the range is too short. So what happens is this neutron interacts with the guys that are closest to him or her, okay? So nucleons interact most strongly with their nearest neighbors. And if I imagine that the strength with which a given nucleon is held inside the nucleus is proportional to how many nucleon neighbors it has, you can see that nucleons on the surface have fewer nearest neighbors than the ones deep down in the middle. Because if you think of this guy, he's got neighbors in all directions if he's really in the center of the nucleus, whereas this one has neighbors on one side but not on the other. So the nucleons on the surface have fewer nearest neighbors and therefore are less tightly bound than the ones in the middle. Just because we're inside a nucleus doesn't mean all the other interactions are turned off. So we have to remember the fact that the protons all have positive electric charges, and as a result, they're repelling each other. So that's another influence that's going to affect that binding energy. It turns out that the strong nuclear force has several symmetries associated with it, which again we'll talk about in a little more detail later. But one of them is that the force between two protons, or between two neutrons, or between a neutron and a proton are almost all identical. Okay? So the strong nuclear force doesn't really discriminate between neutrons and protons. And as a result, all other things being equal, the nuclei would have approximately the same number of neutrons as protons. And then another feature of the nuclear force, which is different than gravity or electromagnetism, is that the fact that the neutrons and protons plays a role in that nuclear force. It turns out when we're starting to assemble nuclei, neutrons like to pair up with opposite spins. So if I am going to put two neutrons into a nucleus, I will put them into the lowest energy states that are available, and remembering that protons, neutrons, electrons have half-integer spin, so they are subject to Fermi-Dirac statistics and they obey the Pauli exclusion principle. That means I can only put one given type of particle into one quantum mechanical state. And so the way I can distinguish the states from one another is, let's say I have a 1s state, a state with principal quantum number 1 and 0 orbital angular momentum. That state can accommodate two neutrons or two protons as long as I put one of the neutrons in with its spin pointed up and the other with its spin pointed down. So there is a spin-spin interaction that is present in the nuclear force, which is absent in other interactions. So neutrons like to pair up like this, protons like to pair up like that. And that'll lead to consequences in the binding energy. So these qualitative sort of arguments lead to something called the semi-empirical mass formula. This was figured out in the 1930s by a guy named Weizsäcker. And so what we do is we write down the equation we had before, which is that the mass of a neutral atom now of an element that has Z protons in its nucleus and a total atomic mass of A, the mass of that atom is Z times the mass of a hydrogen atom plus N times the mass of a neutron minus this binding energy that we're talking about. And what we're talking about now is trying to calculate that binding energy in terms of specific properties of a given nucleus. Okay? Because that binding energy depends on Z and A, and it depends on it in a complicated way. Okay? And if I sort of go through this equation, I can relate it to the factors we just talked about on the previous slide. So the binding energy B is equal to something which is proportional to the volume. Okay? If the nuclear force weren't short range, if every nucleon could see all the other nucleons, it would be directly proportional to the volume, and that would be it. It isn't quite true, but nevertheless, there will be a term which is proportional to the volume. So A is proportional to the volume of the nucleus, the number of neutrons and protons. And there's a coefficient out front that we'll determine later. Then I use the fact from my hand-waving argument that the nucleons on the surface are less tightly bound. So there will be a negative term, something which subtracts away from the binding I would have had if I had a more long-range force. So I have a minus sign, and then I want to have a term which is proportional to the surface area of the sphere. And if I'm saying the volume goes like A, then the surface area is going to go like A to the 2/3. And again, there'll be a coefficient in front of that, A sub s. Then I also have to remember that those protons are all repelling each other. The proton repulsive energy goes as Z squared over R, where R is the radius of the nucleus. And as we're going to see in a little bit, the radius of the nucleus goes like A to the 1/3. So this Coulomb term is going to go like minus another constant A sub C times Z squared over A to the 1/3. Then there's a term called the symmetry term, which is a reflection of this fact that I mentioned. I would, all other things being equal, like to have equal numbers of neutrons and protons. And so the further I get away from n equals Z, the bigger that term is, the less. And then finally, there's that factor that says that the neutrons and protons like to pair up with their spins in opposite directions. That's that pairing term on the right there. So what you do is you take this formula. The functional form is well determined. We've just argued by hand waving that that's what it should look like. What we don't know are those coefficients, AV, AS, AC, AA, and delta. Remember I said this is an experimental science. So what you do then is you go out and measure its mass and plug it into that formula. So you go out and measure m of Z and A. You subtract from it Z times the mass of a hydrogen atom minus n times the mass of a neutron, and what's left is this binding energy. And from that number, from the binding energy in this functional form, you do a fit where you allow these coefficients to vary in such a way as to minimize the discrepancy between the theoretical calculation and the experimental data. And when you do that, you end up with a set of numbers. Okay? That's where these numbers come from doing just what I said. And you don't need to remember what these numbers are. Again, we would give you those. But the point is to be able to use them in a formula like that and calculate masses or something related to masses. The delta term is a little tricky to interpret or to apply. You can see what it says here, that it depends on the nature of the nucleus you're talking about as to how big delta is and what the sign is. So if Z and N are both even, what that means is I'm going to have an even number of neutrons, so the neutrons will all pair up with their spins in opposite directions. And in this case, Z is also even, so the protons will all pair up. That leads to extra binding energy, so delta is positive in that case. If Z and N are both odd, what that means is I've got an odd proton and an odd neutron hanging out. They have no partners to pair up with, and so I lose binding energy. And if A is if A is odd, I have one case, either the neutrons or the protons are paired up, and I've got an odd neutron, or vice versa, so this delta term is 0. So it can be positive, negative, or 0, depending on how many neutrons and protons I've got in the nucleus. This shows you how well it works. So this is a curve just like the one I showed you a minute ago, where it's the binding energy per nucleon versus A. The data points are binding energies per nucleon, and the smooth curve, the line going through it, is the fit that we get with the parameters I just wrote down. So you can see that for most features, it does pretty well. It shows the trend that the binding energy starts out low, it grows, reaches a maximum, and then falls. That's all pretty good. What you notice is there's some bumps. There's a bump here, bump there, bump there, bump there, where the binding energy is significantly larger than would be predicted by this calculation. And if you go back and look at which nuclei they correspond to, they correspond to nuclei with what we call magic numbers, closed shells of either neutrons or protons. And in the function we wrote down, there are just smooth functional terms there. There's nothing that indicates any underlying shell structure or specific numbers that lead to extra stability. So it's not surprising that we end up missing the binding energies there by a significant amount, and we'll see what we need to add later on to correct for that. But the semi-empirical mass formula is very important. It allows you to calculate basic ideas of Q values for nuclear reactions and also which types of radioactive decays will occur as a function of the ZNA of the nucleus. And this is just a sort of schematic showing you how the different terms contribute to the total binding energy. So if I just look at the volume term, the binding energy per nucleon is just a constant, because remember, yeah?
On the previous slide,
yes.
Is there a reason why the formula seems to be slowly
here?
Have lower and lower binding energy per mass?
Right. So remember what you're trying to do in one of these fits is you're trying to minimize the discrepancy between the curve and the data. So if you're high on one side, you'll tend to be low on another. You would have a bad fit if the curve were always above or always below. The fact that you have points on both sides of the curve says it's actually a pretty good fit because it's done the best it can. But what you're pointing out is the fact that this functional form isn't adequate to actually explain the data. You need a lot more terms than that. You need more underlying physics. But I wouldn't worry so much that these are low and those are high. That's really the way it should work. So just getting a feel for how these various terms contribute. So remember the volume term, go back. The volume term is proportional to A, and so if I take the binding energy per nucleon, that means dividing it by A, I would just get a constant. And so the volume term would just be a constant independent of A. When I add in the surface, if you think about a sphere, the more surface area I have relative to the volume, the less binding energy I have. And that will be true most for the lightest nuclei. So I'll get less binding energy for the lighter nuclei, and as the nucleus gets bigger and bigger, the ratio of the volume goes down, and therefore I get more and more binding. When I put in the Coulomb, a similar thing happens as I start cramming more and more protons into the nucleus. Eventually that Coulomb repulsion overcomes the nuclear attraction, and I get less and less binding. And when I put in the symmetry, I get a similar thing. So each one of these components distorts the binding energy curve into something closer to what we actually see. There may be a little point of confusion in the different ways we talk about measuring nuclear masses, and I want to either try to clear it up or even make it more confusing, depending on how you look at it. We talk about the nuclear binding energy, and then you go to the back of Lilly's book, and there's something he calls the mass defect or mass excess, delta. The two are related to one another, but they're not exactly the same thing. So the binding energy is defined from that formula right there that we've just been talking about. Mass excess or mass defect, which is in the table, is called delta, and it's the difference between the actual mass of a given atom of Z and A minus A, where A is the sum of the number of neutrons and protons. All of these things measured in atomic mass units, where remember atomic mass unit is defined to be 1/12 the mass of a neutral carbon atom. So if I take B and I add it to delta, and you might say, why in the heck is he doing that? But hang on a minute. I just add B plus delta. What you notice is the mass of the nucleus actually drops out, because I have a minus m of Z and A and a plus m of Z and A. They cancel out, and I end up with this thing. And so if I just plug in what is the mass of a hydrogen atom in AMU, what is the mass of a neutron in AMU, and so on, I end up with this formula, which just says that the sum of the binding energy and deltas are related, and it just depends on Z and A in this way. So the two are similar, but they're not exactly the same thing. And you can use either one in your calculations. You just don't want to mix them, because they're not exactly the same. Okay. So now I go out and I look. I actually do measurements, and I measure the masses of nuclei. And I want to compare them to the semi-empirical mass formula. And this is where life begins getting complicated in nuclear science, but it also adds to the richness of the field. So first of all, let's take the case where I have a set of nuclei that all have the same A, and A is odd. And the example which Lily picks here is A equals 121. So I have a whole bunch of nuclei that differ from one another in the Z of the nucleus, and hence also the number of neutrons, but the sum of the neutron and proton numbers is all 121. I go out and I measure their masses, and I plot them as a function of the Z of the nucleus. Okay? So Z is increasing this way, N's increasing in the other way, the sum's 121, and on the vertical axis is the mass of the atom that has A and Z in it. And what I find when I look at odd A nuclei is almost always the same. I end up with a curve that looks very much like a parabola. Okay? Each one of those data points represents one particular nucleus. Okay, so here, this is Z48, so that's cadmium, this is tin, this is tellurium, and so on. And what I find is that there is one nucleus which sits at the bottom of the parabola, here, and that is the one nucleus in this particular A chain, as it's called, that will be stable, meaning it doesn't radioactively decay. Why is that? Well, all the guys on this side have more mass, and all the guys on that side have more mass. And remember, nature always tries to go to the lowest energy state, and you can think of this as a potential well, okay, or a hill if you like. Imagine I take a ball and I set it down where that dot is, and I let it go. It's going to fall down the hill. Well, this isn't really a hill in that sense, but nature has a way of lowering the energy from that state, and that's called beta minus decay. Because remember, what happens in beta minus decay is that a neutron turns into a proton. And so if I start out in this nucleus, cadmium-121, and I turn a neutron into a proton, it will increase the proton number to 49, and that turns out to move me down this parabola to lower energy. And all the nuclei on the left-hand side of the bottom of the parabola are neutron-rich. They have too many neutrons for the number of protons they have, and they will all beta minus decay to reach the lowest possible energy state. So the cadmium will turn into, I've forgotten, antimony, I guess it is, and that'll turn into tin, and that'll eventually turn into whatever this is. And then it'll sit there, because it can't reach a lower energy state anymore by beta decay. On the other hand, if I'm to the right of this stable point, I've got too many protons for the number of neutrons. Nature also has a way to correct for that, and that's beta plus decay or electron capture. In both of those processes, what happens is a proton turns into a neutron. So I move down the parabola in this direction. So I start out over here at God knows what that is, and move my way down again until I reach a stable nucleus. So this is a feature that you'll always see for odd A. The points fall on basically one parabola, and if you go back to the semi-empirical mass formula, you can calculate that, and you'll get a curve that looks very much like that smooth curve drawn through there. Okay? So the semi-empirical mass formula predicts that for a given A, if you just let the z's and the other features vary, you'll get a parabola. And it's basically from that z-squared dependence from the Coulomb term that's doing that. That's the major factor there. Okay, so odd A nuclei are relatively simple. You have one parabola. If I go to even A nuclei, things get more complicated, and that's what's shown over here. Now I've got A equals 122. So I've just added a neutron or a proton. What you can see sort of here is that in fact there are two parabolas there. Okay? There's one parabola down here, the lower energy ones, which correspond to even nuclei. Those are nuclei that have both even numbers of protons and even numbers of neutrons. So for example, let's look here. Here's Z of 50. Okay, so that's an even number. What that means is I've got 50 protons in that nucleus, and each pair of neutrons, there'll be 25 pairs of neutrons in that nucleus. They'll all be paired up with their spins in opposite directions. Okay? That leads to extra binding energy because of that pairing term in the semi-empirical mass formula. If I have, again, an even number of A, 122 here, and I now go over here to 51, that means I have 71 neutrons. So I've got an odd number of neutrons and an odd number of protons. Now I have an unpaired proton that doesn't have a partner to pair up with and spin, and similarly for the neutrons. That costs me binding energy. That leads to a less stable nucleus up here. And then when I go over to mass 50, or Z52 rather, again I'm back to even. The protons and neutrons are each all paired up. That leads me to a lower energy state. So I have two parabolas now, one that corresponds to the even nuclei, the lower parabola, and another one that corresponds to the odd nuclei, the upper parabola. And the separation between them is basically due to that pairing term. You can see in a situation like this, I get into an area that's slightly different than what I had over here. It's true that the nuclei on the left of the parabola are still neutron-rich and will tend to beta decay, and the ones on the right-hand side are proton-rich and they'll tend to electron capture or beta plus decay. But I get into a funny situation with a nucleus like this. So if I started out over here at Z of 48, I'll beta minus decay, and that nucleus is not the lowest energy state possible for A equals 122. Okay? This is actually a lower energy state over here. But if I attempt to beta minus decay, I'm blocked because the state I would produce by beta minus decay, is energetically not allowed. It's higher in energy than the parent. And so that beta minus decay can't happen. The slightly unusual situation I get into with these even nuclei is I can get a very rare phenomenon called double beta decay, where this nucleus undergoes two beta decays simultaneously and does manage to reach a lower energy state. It's an incredibly rare process. The half-lives are on the order of 10 to the 20th years, but it's actually been observed in nature, and it only occurs because of this pairing term. And just to show you, this is some evidence that was taken 40 years ago now. What these folks did is they looked at a very old ore that contained the element tellurium in it. Tellurium is one of these elements for which this process, this kind of thing goes on. And what they're actually looking at is a parabola for mass A equals 130, but it would look very much the same. Tellurium 130 would be here, xenon 130 would be here, and there'd be an unstable one or a higher energy one in between that is not reachable by beta decay. And this ore was about 1 billion years old. They heated the ore up and they measured the isotopic abundance of the xenon that came out of it. Xenon is a noble gas, and it's believed that there was very little xenon in the rock when it formed. And they compared the amount of xenon as a function of the A of the xenon isotopes to what you see in normal air. And so these lines you see here are what you expect from normal air, and all the isotopes except one look like normal air. The one which shows a big anomaly is 130. There's a lot more xenon 130 in that rock than there should have been, and this is interpreted to be the result of the double beta decay of tellurium 130 with a half-life of about 2 times 10 to the 21 years. So even though it's very rare, you can see it, and it's a nice reflection of this double parabola business.
So with this, the points on this parabola, would there be a single point?
In 124, it'll look very much like this. There'll be one over here and one over here, and then one high one in the middle, the odd one that's in between.
But at 124, then there should be even. So half of 122 is 61?
Yes. Oh, I'm sorry.
62. So would there be a point at the bottom and 2 points at the top?
Sorry. So it'll be like this. The even one will be here, the odd one will be there, and 63 or 61 will be the one that's high.
Okay, so there's not a bottom, a 62, 62, Z62, and 62 at the bottom?
No, I don't believe so. Z62, N62, that's going to be very neutron deficient. It'll be way over here, I believe, because let's look at this. So this is 50Z, and so N is 72. So 62 for the neutron number is way over here. So for these even guys, you'll usually get something like this, and then there'll be one odd one in the middle. These things are usually labeled stable because the only way they can decay is through this double beta decay, and the process is so slow that these things end up occurring in nature. So if you look at the tellurium isotopes, it turns out there are actually 3 of them that can undergo various kinds of double beta decay, but they all occur naturally because the half-lives are so incredibly long. The half-lives are 10 to the 20th years or longer, and the age of the universe is only 10 to the 10th years, so not many of them have had a chance to decay. Okay, so you're going to see a lot more drawings that look like this over the course of the semester. And just remember that what nature's always trying to do is get to the lowest energy state by whatever means she has available. And if you're talking about a situation like this, it's going to be beta decay. But that restricts you to keeping the A of the nucleus the same. You can make similar plots for nuclei that differ by Z and A, and you'll find situations where you can predict through the semi-empirical mass formula what other kind of decays could happen. For example, alpha decay. You could calculate the mass of a nucleus with Z and A and the mass of a nucleus with Z minus 2 and A minus 4, and the semi-empirical mass formula will tell you which way the decay will go, which nucleus will be lower in energy and hence allowed to alpha decay. So it's not just for beta decay is what I'm trying to say. In atomic physics and chemistry, we make use of ionization energies as a useful tool. It's a way to measure how stable a situation is, how stable an atom or an element is, and how easy it would be to undergo a chemical reaction. Similarly, in nuclear physics, we use proton and neutron separation energies in the same way. So the neutron separation energy is defined to be this quantity I've labeled S sub n. It's the energy required to remove one neutron from a nucleus. Okay? So I imagine I can go in and pick out one neutron, and I ask myself, how much energy do I have to provide to the nucleus to let me do that? Well, I know how to calculate it. The calculation is done the way all Q-value calculations are done. I take the mass of what I end up with. So I start with the nucleus, M, A, and Z. That's the mass of the parent. I pluck a neutron out, and I end up with a nucleus that still has Z protons, but N minus 1 neutrons. So I add the mass of the product, the nucleus with Z and N minus 1, plus the mass of a neutron, because now I've got a free neutron there, and I subtract from that the mass of the parent nucleus, and that's how much energy I would need to put in. In the way I've defined it, that's going to be a positive quantity, okay? It's a negative Q value, meaning I have to put energy in, but just because of the ordering I've put in there, this is going to be a positive number. So the larger that number is, the larger S sub n is, the more energy is required for me to pull that neutron out. And that means the more tightly bound that neutron is. So if I have a very, very tightly bound neutron, it's not going to want to be pulled out. So it will be difficult to do that kind of reaction. On the other hand, the less tightly bound it is, the easier it is to remove. Analogy to what you see in atomic physics, you know for the noble gases, they have closed shells of neutrons, of electrons rather. It's difficult to add or remove an electron from them because their ionization energies are very, very high. The same thing turns out to be true in nuclei, and when we talk about the neutron and proton magic numbers, we'll look at those neutron and proton energies, and we'll see that when we have a closed shell of neutrons, the neutron separation energies get to be very large. And similarly, when we have a closed shell of protons, the proton separation energy will get to be very large, meaning those nuclei are more nuclear stable, more nuclear inert than their neighbors. Similarly, I can define a proton separation energy. That's the energy I need to pull one proton out, and it's defined in the same way. I start with the same parent, Z and N. I rip out a proton, and I'm left behind with a nucleus that has one fewer proton in it. And again, remember to be consistent in the way you calculate these things. Measure all these in atomic mass units, and all the electron masses take care of themselves. Okay. So we've talked about the chart of the nuclides, and I think I've mentioned this really briefly before, but let me just remind you. There are about 3,000 nuclei known. So in that nuclear wall chart with the thing that looks like Saturn, each one of those boxes represents a particular combination of Z and N. There are about 3,000 of them. Of them, only 270 are stable. And just to be a little more careful, I should say, or very long-lived, meaning long enough lived that they're still around today. Of those 270, if you go in and look in detail, 60% of them have both even numbers of protons and neutrons. Okay? That's a reflection of the fact that the nuclear binding energy is stronger, is larger, if I have even Z and even N. So 60% are even, we call them, meaning they have an even number of protons and an even number of neutrons. And that's because of that pairing term. 20% have an even Z and an odd N, and another 20% have an even N and an odd Z. Again, reflecting the fact that nuclei would like to pair up all the neutrons and all the protons, and if I have an even number of protons, the protons will all pair up, and I'll be left with that odd neutron. And similarly, if I have an even number of neutrons, the neutrons will all pair up, I'll have an odd proton. It turns out there are only 5 naturally occurring isotopes that have both odd Z and odd N. Okay, they're the oddballs. And if you like, you can spend a few minutes looking at the nuclear chart and trying to figure out which they are. They're weird in that even though they're not at the bottom of the parabola, for some other reason, they hang around a long time. But there are only 5 of them. Again, reflecting the fact that that pairing term is important, and it's hard to have odd Z and odd N and still be stable and not have some way to decay. Okay. So we've talked about how tightly nuclei are bound. We've alluded to the fact that nuclei have finite sizes. Let's talk a little bit about how you figure that out and how big nuclei really are. So Rutherford, as I said several times, was a clever guy. And in addition to figuring out alpha, beta, gamma radioactivity, he also figured out nuclei weren't point objects. And the way he did it was from what we call a scattering experiment. So after he sorted out that alpha decay produced helium-4 nuclei, he realized he could use those alpha particles to probe what was going on inside an atom. And so he set up experiments where he would have a source of alpha particles and a target containing whatever material he was interested in studying. And he would measure the number of alpha particles that went through that material as a function of the angle on the other side. So, experiment is you have an alpha particle beam, and let's say this is a gold target, and he has some kind of detector sitting over here at an angle, theta, relative to the direction of the beam. And he would measure how many particles he saw as a function of angle. Those were the initial experiments that were done before people had artificial means of accelerating nuclei to high energies to make nuclear reactions happen. In those days, Rutherford had very crude detectors. So actually what he had was a little screen that emitted light when an alpha particle hit it. And he and his students would stand there and look at the screen and count how many times it flashed and measure how many alpha particles hit it as a function of angle. Later on, we made more sophisticated detectors, and we also made machines which can accelerate particles to arbitrary energies, and we can vary not just the angle that the particle comes off at, but the energy with which the alpha particle comes in. And the reason that might be important has to do with the way the alpha particle interacts with the nucleus. So imagine I take an alpha particle and I shoot it at a gold nucleus. Gold has a Z of 79. And let's think about Rutherford's experiment. He's using an alpha particle from a radioactive source. So the energy of the alpha is going to be on the order of 5 MeV. Okay. From what we've talked about already, what's going to happen to that alpha particle as it approaches the gold nucleus? A little louder? Accelerate. It's going to accelerate? Okay. So what's the interaction that the alpha particle will undergo with the nucleus? The first thing that will happen. Of the 4 forces, what's the first thing that's going to happen? The electromagnetic force, okay? Positive charge, they're going to repel each other, okay? That's going to tend to slow the alpha particle down as it gets closer and closer. We haven't talked about this in detail, but remember I did this hand-waving calculation of barrier penetration for alpha decay, and I talked about the Coulomb barrier, the energy that it would take to actually bring the alpha particle and make it touch the surface of a nucleus like gold. Do you remember roughly how much energy that took? 20 MeV, about. And this is a 5 MeV alpha. So classically, the alpha particle can't reach the surface of the nucleus. So classically what would happen is the alpha particle would get to a certain distance and turn around, strictly from the Coulomb force. And there would be no nuclear interaction at all. Now imagine I have a machine that allows me to dial this energy higher and higher. And I can dial it up above 20 million electron volts. What's going to happen then? So now I have enough energy to bring the alpha particle into contact with the nucleus. So in addition to the Coulomb interaction, what else is going to happen? The nuclear force is going to take over, exactly, okay? So now I have two forces, the strong and the electromagnetic. And so if I start out at low energies, I can measure the cross-section, or the probability for the alpha particle to come out. And this is the number of alphas, let's say. I get some sort of smooth curve. It turns out the cross-section or probability, what did I just do? I pulled this out. Sorry. That's there. Now I've done it. That's the first time I managed to do that. Okay. Start over again. Now I've really done it. Hang on a second. Yes. Which cable? This one. Ah, thank you. And that's what I did. Okay. Yes. Come on. Turn this back on. It doesn't like that. I have a feeling it's trying to cool itself off. All right, we'll let it play with itself for a little bit. Hopefully it'll recover. So the number of alphas is a function of energy of the alpha. Will look like that. And then once I get enough energy so that the nuclei can touch, what do you think is going to happen? So the nuclear force takes over. The nuclear force is strong. What's going to happen to that number as a function of where I'm sitting? Going to drop off. You're right, but why? Okay, very good. It could get absorbed. It could get absorbed, exactly, and that would produce fewer. Or something else could happen. The nuclear force is attractive, and remember the electromagnetic force is repulsive. So they have opposite signs. One is tending to make the particles fly apart, the other is trying to bring them close together. And so there's an energy range where the two compete, and although the nuclear force is stronger than the electromagnetic, it has opposite sign, and it also leads to a smaller number. But you're very good to think about them being absorbed. So that is what happens, and if I can eventually get this thing to come back on, hopefully, okay, you'll get to see that. We have all kinds of technical problems in this class. Come on. Yes. Function F8. That is plugged in. Yes, okay. Didn't waste too much time. Except I can't see this anymore. Okay. So this is what you end up seeing, and it's just what we talked about. So what's happening here is we're measuring the cross-section of the probability for an alpha particle to scatter at a fixed angle of 60 degrees. So theta in that drawing is 60 degrees. And as I start out at low energies, the cross-section is large. As I raise the energy, the cross-section falls, the probability falls. And I get a smooth curve until I get to an energy of about 26, 27 million electron volts. And then there's a sharp break. The slope changes dramatically. And that's a reflection of the fact that up until that point, the nuclei, the alpha particle and the lead in this case, never get close enough together to let the nuclear force take over. At this point, I'm right at the point of the two nuclei touching, and the nuclear force does begin to compete, and I end up seeing a smaller cross-section. So although the nuclear force is stronger than the electromagnetic, you might think at first that would lead to a bigger cross-section. It isn't necessarily true. Depends on the nature of the reaction you're studying, and since this is what we just call elastic scattering, meaning the alpha particle comes in and an alpha particle goes out, and I don't change the nature of the target, this cross-section actually falls. And from measuring the position in energy where that break in the curve is, you can infer how big the nuclei are. Because what you're doing is basically measuring the separation when they're just touching each other. And you can figure out the radius that way. Another way to do it is from another kind of scattering. And this has very strong analogies to what you've studied in optics, I hope. So imagine, now I'm talking about light for a minute. I have a light beam, this little red pencil over there. Maybe it's from a laser. And it has a little tiny hole in it. So remember that classically light behaves like a wave. And so if I have an experiment set up like that, where I've got a beam of light and a hole and an opaque screen, and I look somewhere downstream, some distance capital D away, I see an interference pattern. I see a diffraction pattern. I don't just see a bright spot in the middle. I see a set of alternating bright and dark spots, or light and dark rings. Okay? And the position of those maxima and minima, the intensity maxima and minima, is a function of the wavelength of the light and the size of the hole. Okay? And from classical optics, you can write down the positions of these maxima and minima. The height, let's say y from the center there, depends on d, the distance my screen is away from my slit. It depends on the wavelength of the light lambda, and little d, the diameter of the hole. So I can do an experiment like that with nuclei, okay? And I don't know if you studied this in optics, but the situation I've shown you here, where you have a dark screen, a dark wall, if you like, with a little tiny hole in it, and you get a bright spot directly behind it, that's not very surprising. Okay, that's exactly what you'd expect, that where the hole is, you'd expect to see a bright spot of light. On the other hand, if you do the opposite situation, you have a solid object where that hole is, okay, and no screen. Okay, so I just have a little sphere or a little circular disk sitting where that hole is. And you do the same experiment. Believe it or not, there's a bright spot right at 0 degrees. Okay, and again, it's an interference effect. It has to do with the light interfering as it goes around that dark object, and you get a bright spot right in the middle, and again, a series of maxima and minima. So if I do it with nuclei, I can expect to see the same thing. So what I do here is I need to have a probe which can probe the size of the nucleus, and we know that nuclei are on the order of femtometers in size, so I'm going to need a probe that has a wavelength comparable or shorter than that. And one way it's done is to use electrons. So I take electrons, I accelerate them to very, very high energy, where they're very relativistic. So in this example, we've picked 420 million electron volts for the kinetic energy of the electron. It's much, much larger than the rest mass energy of the electron. And so I can use the extreme relativistic kinematics and say that the energy of that electron is its momentum times the speed of light. And I can calculate the wavelength associated with that electron. It's just h, Planck's constant, divided by the momentum. And I plug in the numbers, and it turns out the wavelength of a 420 MeV electron is 3 femtometers. Okay? And so then I can shoot these electrons at a target, and I measure the number of scattered electrons as a function of the angle. So this is the number of scattered electrons, this is the angle at which I measure it, and there are a bunch of different curves here, but for the moment let's stare at the curve that has the solid black points on them. These correspond to shooting electrons at the nucleus oxygen 16. And what I see is there's a lot of counts at 0 degrees, then there's a minimum, then there's a maximum again, and then another minimum. And if you think about it, that's the same kind of interference pattern I would have gotten with optical photons. So these electrons are diffracting around that dark object, that oxygen nucleus, and it turns out from the position of either the maxima or the minima, you can infer the size of the object that it went around. And by measuring the position of this minimum here, I find that this corresponds to an angle of 45 degrees. I can solve for the diameter of the O16, and I get 2.6 femtometers. I do the same experiment. I shoot 420 million electron volt electrons at carbon-12, and I get this set of data. And you can see the position of the first minimum is moved out a little bit. It's more like 50 degrees instead of 45. That's because the carbon-12 is smaller, and the first minimum is at a larger angle, according to that formula. So from electron scattering experiments, you also get a handle on how big atomic nuclei are. And if you do this over a series of nuclei, from light to heavy, you end up getting a measurement that looks like this. Now, this is more detailed than simply the radius. This is showing you where the electric charges are that these electrons are scattering off of. And what we find is that for almost all nuclei, the charge density, which really means the number of protons in the nucleus as a function of volume, is a constant out to a certain radius, and then it falls kind of quickly after that. And you can see that as I go from calcium to cobalt to antimony to bismuth, the nuclei get bigger and bigger. But to first order, the density of charge in the nucleus is more or less the same, and then it falls off. And we can use that as a way to size of the nuclei. So that's one way. So we've talked about two ways now, the alpha scattering, the electron scattering. Another way you can get a handle on atomic radii or nuclear radii has to do with looking at X-ray transitions. So remember, X-rays are emitted when an electron moves from one bound state to another. And that depends on how many protons are in the nucleus. But it also depends on how that charge is distributed in the nucleus. The nuclei are not point objects. We know they have a finite size. And these electrons sense the distribution of charges inside the nuclei. And so you end up with small differences in X-ray energies depending on the radius of nuclei. So if you look at, let's say, tin, the element tin has about 10 stable isotopes. Each one of those isotopes has a slightly different nuclear radius. If you measure the energies of the tin X-rays as a function of the A of the tin nucleus, you'll find they're all slightly different because the nuclear radii are slightly different. But the shifts are very, very small, and in fact, so here's a plot. It's not tin, it's mercury. These are the differences in X-ray energies as a function of the A of the mercury nucleus. So they all have the same Z, but what's differing is the N. So the radii are different. So the X-ray energies are very, very slightly different, and you probably can't read it. Those are fractions of an electron volt. Okay? But if you go to the chart you've got in your hands, you'll see, and maybe you know already, that the electron has a heavy cousin called the muon. It looks and smells and tastes very much like an electron, but it's 200 times heavier. And you can make atoms that have one or more of the electrons replaced by a muon. These are called muonic atoms. And because the mass of the muon is so much heavier than that of an electron, the radius of the orbit that the muon goes in is much, much smaller. It's 200 times smaller. And so it spends a lot of time inside the nucleus sensing that nuclear volume much more than electrons do. And so if you measure the X-rays of these muonic atoms, the shifts are much, much larger. And that's what's being shown over here. These are muonic X-rays in iron, and the shifts are not electron volts anymore. They're thousands of electron volts. This is iron 54, 56, 58. You can see these peaks. This is a 1,000 electron volts, and that's a reflection of the fact that the muon is spending much more time in the nuclear volume. So the point is we have a bunch of different probes that all allow us to study nuclear radii and figure out that the nuclear density is about constant, the radius of a nucleus goes like a to the 1/3, and the proportionality constant goes out front is a number something like 1.25 femtometers. So if we want to calculate the size of a lead nucleus, we say lead maybe has A of 208. We plug 208 into that, take the cube root of it, multiply by 1.25. That's a good estimate for how big that nucleus is. Okay? And we'll use that over and over again throughout the rest of the semester. Okay, this is a good place to stop with the discussion of nuclear radii. We'll go on and start talking about angular momentum in nuclear systems in a little bit more detail. See you Wednesday.